Mr. B, and this is the Learning Zone. In this video, I will explain how to calculate the wavelength and the frequency of electromagnetic radiation. Electromagnetic radiation is also known as radiant energy or simply light energy. When learning a new topic, it is always important to become familiar with the terms associated with that topic. In this video, you will encounter the following terms. Wavelength, which is the distance between two peaks of a wave. Frequency, which is a measure of the number of waves that pass a particular point per second. Amplitude, which is the height of a wave. Nanometer, which is equal to 1 times 10 to the minus 9 meter. Electromagnetic radiation, which is of course radiant energy. The visible spectrum is the portion of electromagnetic radiation that is detectable by the human eye. Cycles per second are the units used for frequency, and so are hertz. Electromagnetic radiation will travel in a wave where the power or the strength of the wave is related to the wavelength and the frequency of the wave. Waves may be as long as 1 times 10 to the 4 meters, which represents AM radio, or as short as 1 times 10 to the minus 14 meters, which represents gamma radiation. Only a small portion of electromagnetic radiation is visible to the human eye. This radiation has a wavelength from 1 times 10 to the minus 7 meters or 700 nanometers to 4 times 10 to the minus 7 meters or 400 nanometers. Notice also that as the wavelength increases, the frequency will decrease, and vice versa. This means that the wavelength and the frequency of a wave are inversely proportional. Electromagnetic waves also consist of two field components, where there is an electrical field component as well as a magnetic field component. Thus the name electromagnetic radiation. In a vacuum, light will travel at a speed of 186,000 miles per second. The formula, or the equation for the speed of light, is written as follows, where c, which represents the speed of light, is equal to the wavelength times the frequency. Of course, in science, the British system is never used in a calculation. The speed of light in meters has been calculated to be 3.0 times 10 to the 8th meters per second. Inserting this constant into the formula generates the following, where 3.0 times 10 to the 8th meters per second is equal to lambda times nu, where the units for lambda are meters and the units for nu are reciprocal seconds. Now let's use the speed of light equation to solve for the frequency of an electromagnetic wave. Consider the following. What is the frequency of radiation whose wavelength is 589 nanometers? The first step is to rewrite the speed of light equation, where the speed of light c is equal to wavelength lambda times the frequency nu. The units for the speed of light are meters per second. Therefore, the 589 nanometers must be converted to meters. To do so, multiply 589 nanometers by 1 times 10 to the minus 9 meter per nanometer. This will equal 5.89 times 10 to the minus 7 meter. Now rearrange the speed of light equation, where frequency is equal to the speed of light, c, divided by the wavelength, lambda. Inputting the data generates the following, where the frequency is equal to 3.0 times 10 to the 8 meter per second divided by 5.89 times 10 to the minus 7 meter. And of course, solving the equation generates the following result, where frequency is equal to 5.1 times 10 to the 14 second minus 1. The units of frequency may be written as second minus 1, reciprocal seconds, hertz, or cycles per second. Let's end the lesson with a simple wavelength calculation. Consider the following. What is a wavelength in nanometers of radiation that has a frequency of 1.2 times 10 to the 13 reciprocal seconds? Of course, the first step is to rewrite the speed of light equation. C is equal to lambda nu. Then rearrange the equation to solve for lambda, where lambda is equal to c divided by nu. Inserting the data generates the following, where lambda is equal to 3.0 times 10 to the 8 meters per second divided by 1.2 times 10 to the 13 reciprocal seconds. And lambda will equal 2.5 times 10 to the minus 5 meters. The practice problem asks to solve the wavelength in terms of nanometers. To do so, multiply 2.5 times 10 to the minus 5 meters times 1.0 times 10 to the 9 nanometers per meter. In nanometers, the wavelength will then become 2.5 times 10 to the 4 nanometers, or 25,000 nanometers. This particular wavelength will place the radiation in the infrared range. This concludes my explanation of how to determine the wavelength or the frequency of electromagnetic radiation using the speed of light equation. Hopefully this video has been helpful. Thanks for watching.